No, me neither. I feel like only LLVM transforms before the. Yeah, but we're not gonna use LLVM for like
Okay.
2 more months.
Hello, everyone. Welcome to the first embedded team meeting. Thank you all for coming. We're gonna get started now, but basically, just a quick introduction of ourselves. So I'm Min. Last year I was the SIGPwny president, and I was also the embedded team lead. This time I'm just doing embedded team. I will be graduating this semester from the BSMCS program. So I'm just kind of here to help the transition go smoothly to Jake. I've been involved in SIGPwny's ECTF team since 2023, so I've done ECTF for 3 years now. And then, fun fact, I rickrolled my high school by hacking the projectors. And I have a blog post if you guys want to see that. And here's Jake.
Yeah, so I been a SIGPwny admin and I'm embedded co-lead. I was an embedded co-lead for Induce 2024 and 2025. I've also been competing in 2023 like Min. I am separately a CS and math major, and fun fact, I was actually rejected from this school that I took a job for. So I can talk a little bit about like what embedded system is. So Wikipedia definition is like very general, but fairly comprehensive. So it says embedded system is specialized computer system. It is a combination of computer processor, computer memory, and input-output peripheral devices. And the part that differentiates it, that has a dedicated function within a larger mechanical or electronic system. So the kind of the critical parts is that it's specialized and that it's within some larger system. So maybe some examples are from various levels of importance as far as the security properties. Well, voting machines, those are embedded systems, part of a larger system, and the software is very specialized. Cars, there's a lot of embedded systems in that. So a lot of the vehicle controls are embedded systems, entertainment system as well. Traffic lights as well. Security cameras, medical devices, really important areas such as an insulin pump. And you know, a lot of military applications like missiles. Oh,
Oh no, the audio doesn't work here. Oh my god. Well,
you clearly know what it's saying.
yeah, okay. Well, the missile, yes. I'm sure you guys have seen that sketch before, but
yeah, maybe I'll field a question here. Like, what are some other examples of embedded systems that you could think of? Yeah, sure.
Embedded Linux.
Sure. Yeah, that's like kind of some software that might run on one. Yeah. Sure.
Pacemaker.
Pacemaker, yeah, medical devices. Any other like maybe more unconventional ideas? Sure.
well, like garage door.
Sure. Yeah, that's. I think I've seen some security research in that actually, but yeah. Yeah. Thermostat, yeah.
Yep. Oh yeah, it's there, but we got it. We got them all. Let's go. Thank you.
Sure. Yeah.
Now I have a counter question. Why don't we use like a general computing system? Like, why can't we just use, let's say a PC for my car entertainment system? Yeah.
Well, certain things have very strict time deadlines, so like we don't have any specific software in the general like OS that will maybe block or like do things that don't have to.
Yeah, that's a great point. So like if you use a general operating system like Windows or Linux, those are operating systems built to do a lot of different tasks at the same time. And so they don't meet the requirements of what we call a real-time operating system, or basically a system that acts as instantly as possible because it needs to react to some input device. So if you've heard of RTOS, RTOS is a real-time operating system, so usually embedded devices will be built on top of that. Cool.
Yeah, so then kind of maybe making this a little bit more specific, so that's a very broad and comprehensive definition. Some common things is like, yeah, it's part of a larger device, right? So maybe you think of like a robot or something, particular one that interfaces with sensors, or maybe actuates mechanical things, right? So, you know, an example of that would be like a car, right? It has both of those sensors and the actual driving of the car. often you're in a very like low power or resource constrained environment. So like if you're battery powered, you can't run a general purpose computer on like very small battery for a long time. And like microcontrollers in particular are very resource constrained, and you'll get a closer feel for that when we actually start developing on them. But you're talking about like kilobytes of memory and things like it. It's not a general purpose computer. And then, so what is embedded team? We focus on security of embedded systems primarily and IoT devices. Particularly, like, there's a lot of things that like make embedded security different than general securities, where hardware and software come together. So for general like software security, a lot of those things still do transfer over to embedded devices. I mean, a lot of embedded devices run web servers and things, right? So there is quite a lot of similarity, but there's unique aspects to embedded security that involve interfacing with the hardware. So that could also just be like different classes of software vulnerability that have to do with the kind of peripherals that embedded devices have. Peripherals meaning like communicating over wires, things like that. But then there are also classes of attacks that we'll talk about more later that specifically involve attacking the physical device that it's running on. So there are vulnerabilities because an attacker may have physical access to the device that, it's just not something that you think of when you're just designing software. So in particular, we play in competitions related to embedded security. We'll talk about two of those today, Seesaw and ECTF. And then sometimes we also work on larger projects involved with research. So some reasons for why you might want to join the embedded team. It's one of the best ways to learn about programming really low-level systems. So like if you're interested in like understanding kind of what's going on, like even below like your operating system, it'd be a good way to learn more about that. And also they're a lot smaller and less complex, like kind of as I was alluding to earlier. So it's a lot easier to actually build something all the way down, like building a whole operating system for general purpose computer. That's like hard, right? A lot going on, but just making like a light blink on a microcontroller, you're going all the way down to the bare metal, but you don't have to. There's like not that much going on. So I think, at least in my mind, it's a lot easier to understand much broader, a much maybe like a broader proportion of what's going on a microcontroller than you would on like a general purpose. It's a lot easier to get a good idea from a lot of what's happening quickly. Then another reason is learn how to apply adversarial mindset in a new domain, right? So SIGPwny generally, we're going to talk about a lot of software security. This domain, you'll see it's a little bit different, right? Like I was linked to with the hardware attacks. So you get to kind of practice building this skill in a different way.
I'm actually curious, how many of you here have like done work with embedded systems before? I'm not expecting a lot of hands, but okay, there's a few. But I presume that a lot of you haven't done really security related work in there. So practicing adversarial mindset is in like somewhere completely different, somewhere completely new that you never touched on, is very good, because then you can apply that skill later on in life, no matter what you're working on. So this is why I love embedded team, just because like there's so many like weird new things to learn about embedded security. And like it's just kind of fun because you can just buy this stuff and do it yourself too. Yeah.
Yeah, and then most importantly, we need to beat Purdue and CMU. Purdue is no good.
At least Purdue.
So if you guys haven't seen, we have, if you've been in the ACM room before, we have a sort of table in the ACM back room. So ACM has 3 rooms. You've probably seen the front room at least, but if you go to the doors through ACM, there's going to be a middle room and there's going to be a back room. And the back room kind of is used for storage, and there's lockers and things like that. But it also has our table where we have our embedded equipment. So this is all SIGPwny's property. Feel free to use it. Make sure you ask for permission if you're going to like remove some things from some parts. But if you're ever interested in using the equipment, we have like the oscilloscope, or we have like probes and multimeters. If you're ever feeling inspired, you can just show up there, and we have the equipment out there. It's a bit of a mess right now, admittedly, that will be rectified at some point.
It looks a little more like this.
So this was the aftermath of ECTF from last year. Yeah.
Wait, so what's the location of the one?
So right across the hall here, this ACM room. You can't miss it. There's there's usually people in there. There's a little pedestal outside that has the ACM logo on it. But that's the front room immediately. And if you go through the doors, you can get to the back room and then you can find this table.
Yeah, there's a middle room intervening. There's 3 rooms.
Yeah, there's a middle room in there as well. So ACM is a very cool space. There's a lot of room to work. I spend a lot of time there just kind of doing my own work and chilling with people. So it's kind of nice too for that. Yeah. So I'm gonna quickly go over some of the meetings that we have planned for the semester. So a lot of the main competition that we play in, which is ECTF, happens in the spring. So the idea is that in the fall, we're trying to get you all sort of onboarded, trying to basically teach you a lot of the things you need to know about embedded systems. So that way you can, if you're interested in doing ECTF, you can jump right into that. We have 3 meetings sort of for the first few Mondays, which are kind of like intro meetings. So Embedded 101 is going to be fundamentals. We're going to be talking about microcontrollers, the components of embedded systems like flash chips, maybe just some general computing concepts as well. Embedded 102, we're going to sort of talk about microcontroller programming. So we're going to basically give you microcontrollers. We have a kind of a ton that we've accumulated over our time. And we're going to basically have you set up a hello world. So you can run code and build it right onto a hardware device from your computer. So hopefully that is cool, and you'll hopefully it won't be too annoying because some systems will have different setups, but we'll figure that out. And then Embedded 103 is where we're going to touch a little bit more on the hardware. So we're going to have some breadboards, some wires, and we'll probably the most basic example we'll have is using programming a microcontroller to control an LED on a breadboard. Hopefully that's fun, and that sort of teaches you the concepts of electrical engineering, especially if you're coming from a CS background. For the record, I am a CS major, so I've never touched embedded systems before embedded team. I basically did all this sort of self-taught, and also with the help of more qualified people than me. So we're trying to speed up that process by having these first few meetings be kind of very intro focused. And then we're going to get into a little bit more of the security side of embedded. So these 3 meetings, we might actually turn into some sort of kind of a walkthrough of what ECTF looks like. So these 3 meetings actually sort of are like the different stages of the ECTF competition. So what we might do is we'll have you pair up, and then you guys will sort of design a very basic secure embedded system. Not necessarily implement it, but just so that way you can see kind of what that process looks like. So the first thing we have is secure protocol design, which is where, I have a system, I want to build it, how do I make it secure? So we talk about the design of that. We're going to talk about software security from perspective of vulnerabilities and common issues like memory leaks, memory vulnerabilities, memory bugs that can cause someone to exploit your system. And so that will be a little bit slightly more advanced. It will also coincide right around when SIGPwny General will do its binary exploitation or PWN meetings. So we highly recommend that you also attend SIGPwny's PWN meetings when they come out, because they'll kind of give it a little bit more background about exploiting memory vulnerabilities. And then lastly, we are going to advance that further by attacking maybe some of the secure protocols that you guys have developed. right? And talking about attacking maybe logic errors, sort of logic bugs, attacking weak cryptographic implementations, or just doing memory corruption exploitation based on software security meeting. And then finally, we'll get into the more advanced topics, which touch a lot more on hardware. Side channel attacks are basically where the hardware can reveal information about what the software is doing, and that's why we call it a side channel, because you're using other means to bypass maybe software that's secure in theory, but not in hardware. And there's things that you can do, like you can look at the power level of the chip as it computes, right? Because if you want to change bits in memory, inherently, you have to use energy to change a bit from a 1 to a 0. That's like physics. So if you're changing more 1s to 0s, you're using more energy. So you'll see power spikes like that. And that's a power analysis side channel. We'll go over more into side channels in the coming future. We'll talk about firmware security. So this is different from software security because software security is like kind of the application code that you're writing and how to make that secure. Firmware security is how do you make sure that the hardware is doing what it's doing, running your software. So we'll talk about things like bootloaders, secure bootloaders. We'll also draw connections to things like, if you have an iPhone, you have a secure enclave. There's an equivalent on Google Android. Windows has TPM chips. I'm sure maybe some of you have heard of that if you're into like that kind of stuff. And then there's some really cool things in firmware security as well related to exploits there, because you're basically, if you can attack the bootloader, you can attack any code that's running on top of the bootloader, because once you've compromised that, you've compromised pretty much the whole embedded system.
Do you want to define what like bootloader is?
So the bootloader is a code that runs before your code runs. Just to clarify. So if you can compromise that step, then you can run maybe malicious code. And then we're going to talk about one of the more advanced hardware attacks, which is fault injection and voltage switching. So this is where physics really comes into play. Basically, you can mess with the power levels of a chip as it's running, and you can cause it to misbehave. You can corrupt some values in memory, you can skip instructions, and by doing that, you can, like very precisely, you can get the system to do something else, like maybe bypass a password check. So that's a very fun meeting, and it'll be very, it will be more of a demo, because unfortunately a lot of tooling requires expensive equipment, which we don't have a lot of, but we'll be showing it all. And then we have embedded Rust. So throughout most of the meetings, we'll be using embedded C. That's pretty much the industry standard. But when we get into software security, you'll learn about memory bugs and how Rust can fix those. So we use embedded Rust for our designs in the future, and we'll sort of give a brief crash course there. Does anyone have any questions about any of the meetings that I've listed here? Okay, yeah.
Are these all planned to be on Mondays, or are the times going to vary?
Yeah, so these are all going to be planned for Mondays. So they're going to be presented in order that they are here. We might move some things around. We might even drop a meeting depending on who the scheduling and conflicts and things like that. But for the most part, these will all be on Monday meetings. And yeah. Yep.
And not exactly a meeting question, but do you guys ever deal with FPGAs?
So actually the tool that we use for fault injection and voltage switching is an FPGA. We don't really use we don't have we don't teach FPGAs. We don't have like an actual thing dedicated to FPGAs, and you're not going to be actually programming the FPGA when you're using this sort of tool. But maybe we'll like bring that into the future.
It's pre-written by SIGPwny.
Yeah.
Pre-written.
Yeah, the tooling that, like, he's talking about a tool that we use for like fault injection. It has an FPGA on there with firmware that's already written for this purpose, but yeah, it's probably not something we're focusing on right now. But,
Yeah. I probably recommend honestly just taking, was it EC 385, E385, yeah, because that's where you learn about FPGAs, and that's probably a better place to learn about it than like club meeting. I'm gonna be really honest with you.
although a lot of the things that we talk about in embedded security, I don't know if we have a course like this.
Yeah, like for example, even microcontroller programming, there isn't a proper course here that teaches you microcontroller programming. You'll do systems programming, and you'll like program. I guess it's MIPS now. Before it was x86. Yeah, we do cover like things that aren't in the EC or CS curriculum. So yeah. Okay. All right, so I completely forgot to make the slide for this. So we're going to talk about it at the end, but there is this thing called the Seesaw Embedded Security Challenge. Seesaw is short for Cybersecurity Awareness Week. The normal Seesaw CTF, which the CTF team is going to, like, you are invited because everyone can join CTF team. There's going to be a CTF this Friday. And that's just going to be kind of like web security, binary exploitation, cryptography. It's beginner friendly, so we highly encourage you guys all to join this Friday. It's a weekend long competition, but we'll have like a room somewhere in Siebel where you guys can meet. But Seesaw Embedded Security Challenge is like sort of a separate competition run by the same organizers. And this one is sort of a like 2-month long competition. And that runs this fall. Team size is limited to 4. And we're probably going to keep like a limited number of teams just because we don't want to like overload the organizers with teams. So if you feel you're really interested or you have background about embedded security and you want to do the Seesaw ESC, I'll post an announcement later and you guys can sort of apply for that. Again, because it's 2 months long, we're going to have some commitment needed for that. But basically the challenge I'll talk about later, but it's going to be related to voltage switching actually. So if you guys want to get jump start on that, that'll be a good place to do it. Yeah.
So you're saying there's two, there's a 2-month long one and there's the weekend long one. Is the
Yeah.
weekend long one false CTF or is that different?
No, so the weekend long one is a Seesaw CTF, which is like Seesaw's, that's run by NYU. That's just sort of like a general CTF. And then this one is specifically for embedded security. So they have 2 competitions that they run. They actually have a lot more competitions. There's like a 3D printing one, an LLM one. There's a few different ones. Yeah. Yeah, there's also a research project one. There's a research competition. So we just do this because if you qualify, you get to go to New York for free. So they expense all the plane tickets and stuff. Yeah.
Will you send more info about both of them on Discord?
Yes, I will send more information about both of these on Discord.
And registration is still open for both of them.
So for Seesaw CTF, we're registered as SIGPwny. We're going to be playing as one big team because that's unlimited team size. For this is for person team limit.
Yeah, we'll probably have multiple teams for that reason.
We will have multiple teams.
There were like 4 Georgia Tech teams last year. There's like 4. They sent like 4 of them last year.
I think there was 2 that showed it, but you might be right. Yeah.
4 of them would be sense.
Yeah. But now we're going to talk about the big competition that we're sort of gearing towards, because this is like kind of the most exciting one. It teaches you a lot. It's why I'm in embedded security in the first place. So that's MITRE ECTF 2026. So what is ECTF? Is short for embedded capture the flag. Last year, there was around like 160 universities and high schools competing. They're mostly universities. There's like a few, crack high schoolers that will join in. And basically what you do is you build a secure embedded system based on the organizer's functional and security requirements. And the organizer is MITRE, who is a government contractor based in Virginia. Everyone has to implement the functional requirements of the system, but you are responsible for making sure that the security requirements are met, and you earn points by defending your system and also by breaking other teams' security requirements. And the general schedule looks like this, where you have the competition starting in January. You have a month before the attack phase begins. And then you have like 2 months for the attack phase. Yeah. You want to take this?
Sure, yeah. So yeah, the first phase, that kind of like first month or so, well, it can actually spill over into the attack phase. You join the attack phase when you submit your completed design. But the design phase, the goal is to convert the organizer's requirements, both functional and security, hopefully, into design. So the way that we've kind of been doing this traditionally and found useful is to specify like fully what your design looks like. So that would be the protocol and cryptographic methods. Some principles is not an exhaustive list, is defense in depth. So redundant security measures hedge against the vulnerability in either the implementation or even the design choice at the abstract level. And then kind of what this allows us to do is we can audit the abstract design against the particular security requirements before we've actually implemented it. A lot of time when we've actually implemented something in software, it's it's a little harder than if you have it on a whiteboard to make changes to it. So yeah, we spend a lot of time like brainstorming the ideas and trying to make the most robust design that we can before we've written anything. So then after we have something that we're fairly comfortable and confident in, we have to implement the design. And one thing that we're not really done with the security at that point. Like you might think that, but it's only really from a software perspective at that point. But not even all of this, like until you've written the software, you don't really know if you made a mistake in implementing it or something like that. So we use Rust for its safety. A lot of teams use C. So for the most part during attack phase, we'll probably be working on OSC. And kind of as I was saying earlier, the concrete design has to be secure in both software and in hardware, because they will have access to the hardware which it's running on, and they can do anything. Like anything to that hardware is in scope. So like, yeah, like some software vulnerabilities, like there's common ones I think we talk about a little bit later, but particular the hardware is a little bit more complicated, right? Because as we were talking about earlier, like running it on physical hardware is different from this abstract model of the machine, right? Because your machine now might not execute exactly, like in the case of fall injector, it might not actually execute what you've written. It might do something slightly different. So you have to guard against this and be careful. So yeah, I guess now we can talk about the attack phase. So kind of the goal is to break the security requirements. Functional requirements have been verified by the organizer before the team is allowed to submit their design. So points are awarded roughly for each requirement for each team that you compromised. In a single vulnerability, you might compromise all the requirements or many of them. This is actually fairly common that you'll see, like you discover something and full clear for a team. Well, some creativity is required because there's a lot in scope, right? It's not even just the software, it's the hardware as well. And in previous years, there's been like multiple of these things interacting with each other. So it's a lot of potential attacks that are plausible. So some examples of typical vulnerabilities, typical like C on safety. So buffer overflow, integer overflow. Buffer overflow is like when you read memory outside of the originally allocated space for that buffer. And then integer overflow, which is, when you reach the top or bottom, well, I guess bottom of the underflow, when you reach the top of the representable integers, it'll go back down to 0. Some bad crypto. SIGPwny, I think, teaches crypto meetings. Yeah, we teach all of these. A bit more advanced, but a lot of ECTF is actually designing secure cryptographic protocols. So you'll see a lot of vulnerabilities, especially ones that are worth more points because less people are able to pull them off, have to do with like bad crypto implementation. Additionally, like a simple like software attack would be like timing side channel. So for instance, mem compare, it'll go maybe like word by word or byte by byte to like verify each byte is matching something. So if you have like a password or something, you go byte by byte. The more characters you've gotten correct, the longer it will continue through the loop until it breaks out. So if you do this enough times, you can actually find something statistically relevant. So instead of having to guess the whole password, you can go one letter at a time, which, you know, from exponential to linear time. So that's pretty important. And then hardware attacks. So this is what's kind of hard, and we're the only other team besides CMU who I believe have executed this in the competition successfully. So in particular, fault injection is kind of what we're saying. You can skip an instruction, do something else than what was originally intended. So maybe corrupt some memory value. And then also another idea that I don't think anyone has done in the competition is power analysis. So as the chip is executing, depending on what data it's executing over or what instruction it's executing, has a different characteristic for how much power it's drawn. So again, with statistics, you can get something statistically relevant that will indicate what is happening on the chip or what data it's processing. So for cryptography, if it's encrypting something and the power that it draws depends on the key, you can start to get what the key was using to do the encryption is. So like in the abstract model of what it's computing, you're like, okay, yeah, the input, like the output, you can't figure out anything about the input. Like this is kind of the abstract idea of what cryptography is. The physical implementation of it has a totally different security profile because it's running in hardware, which can be observed and it has physical effects.
Yeah. I will also point out that like there's a lot of things that goes into design and attack phase. Like you can see there's buffer overflows, like that's pwn. We have cryptography, and we have like completely new classes of security, like hardware attacks. I will say that I'm not like the strongest math person, and I don't really like cryptography, but through ECTF, I was able to like actually understand like, oh, this is why we do this in cryptography and why we need this. And like it teaches you, like this is actually something I wanted to put on the previous slide for like why you should do embedded team. Like you can learn things like cryptography and be happy with it and not like lose your mind because you don't understand the math. You also lose your mind, but it's much more satisfying when you get to break somebody else's design because you did the math. Yeah, so just for reference, here's a list of some of the past competitions. So 2023 was when we did a car lock system. So you had like a key fob that needed to unlock a car. Now again, this is all abstracted as like microcontrollers, so you don't actually have a car. But you would write code as if you were writing it for a microcontroller for a car. And you would need to make sure the key fob securing unlocks the car. I can't just record a communication and replay that to unlock the car again later on as an attacker. And 2023 also had this thing where like, oh, maybe I want my key fob to also turn on the heater remotely. And maybe as a manufacturer, I was like, no, screw you, I'm going to make you pay extra for that. So you have to implement car DLC. 2024, we did a medical device. So basically, we wanted to build a modular system, which takes some components. So you have like an example of an insulin pump. You have the main processor, which does all the collection of data and decides when you need insulin. You have a sensor component. You have the actuator, which actually injects insulin. And so like those are like three components, right? And so the idea is that you want to be able to like sort of replace components, and you only want to add authenticated like legitimate components. So that was a lot of cryptography then. And it was also a lot of pwn because the organizers put a backdoor in the library that everyone was using. So
Wait, so why didn't we do that for 2025?
You're not
Well,
allowed to.
you're not allowed to.
They're allowed to, but
They're
why-
allowed, yes.
So the organizers basically for all the competitions, they will give a reference design. It fully implements the functional requirements, but it does not implement any of the security requirements. So it's basically use at your own risk.
Yeah, it's often hilariously bad.
It's really bad. So, but what most teams end up doing is they just use that design and they try to fix as many of the vulnerabilities as they can. That usually doesn't work. Which is why we also do a full rewrite in Rust. And then last year we did a satellite TV. So you have basically subscriptions to channels. You want to encrypt the stream so that way people can't just like steal your streams from your satellite. So you need to have a valid subscription and a valid device in order to read encrypted frames.
Yeah, the cryptography part came in because like a satellite is broadcasting everywhere, so everyone can read the signal, but
Yeah.
the idea is that they shouldn't be able to actually get the frame content, like the TV show that you're actually watching, unless you paid for a subscription valid for that time period.
Yeah. So that has some very interesting cryptographic challenges. Like, cause like, let's say somebody hacked your embedded device and stole the secret, and now you distribute that secret on the web, and now everyone can decrypt your encrypted streams. So there's ways to actually defend this, and that was very interesting and cool. I saw a question. Yeah. So we were the first team, I want to say, to use Rust in 2023. There might have been.
There were others. It was
Oh no, there was one other team. It was University UCSC. And then 2024, it was only us and Purdue. And so say that again. So I think there was like a transition in leadership, and then people were like, "Oh, I don't know how to write Rust. I'm gonna write C." They come back 2025. They come back to Rust. Just FYI. But 2024 and 2025 use the same microcontroller. So what we actually did was we wrote a hardware abstraction layer in Rust that all the other teams could use for 2025. So we actually ended up allowing like basically, so we went from 2 teams in 2024 using Rust to 9 teams in 2025 using Rust because we did that. So yeah, we're very much open about like helping people design systems securely, and so we open source a lot of our kind of projects because unlike some other teams, specifically CMU very clearly does not distribute their source code with a license, so you can't redistribute it, or they will also be mad if you use their code. So yeah, exactly.
That's why we're like no
if you
Why? Go back to
Yeah.
that why.
but yeah. So I just have this image here just to kind of show off like this is not even like super related to the actual attacks and the systems that we were attacking last year. This is like infrastructure we wanted to build out just so we could attack faster. So this was like even like more of like just a general CS project. It wasn't even a lot of embedded. And so we had like cloud stuff and AWS and things like that. So that's also something that we do.
Yeah, the point of this is that many teams had like predictable vulnerabilities that you could actually script, and there are points for getting it in first. So there's actually a big race last year to be able to attack teams as quickly as possible. So that's where this automation.
Yeah. So I just want to say that even if you feel like you aren't the strongest in terms of embedded programming or like working on the actual like code for our microcontrollers, like there's a ton of stuff that you can be doing as well, like building our infrastructure, or like we wrote this in O and Go, for example. So that's also something you could learn. So now we're going to just quickly talk about the 2026 competition. So registration has opened and we will register as a team. But they gave us a little sneak peek. So it's very sort of vague, but the teams will design and implement a secure storage solution for a chip foundry. Does anyone here know what a chip foundry is? I'm gonna pick you.
Eight?
Yeah, you.
Okay. Special. I mean, basically, chip foundry, it's think of like TSMC or Intel. They basically specialize in making all the chips that run their computers and all that sort of thing.
Yeah. So basically, chip foundry, just fancy name for the chip factory. But basically, you want to build a system which prevents leakage of sensitive chip designs. And you can see there's a keyword roles. So we're likely going to have to implement a system with role-based access control, where like certain users can have more permissions over another user and can see some things. So that will be interesting to implement as well. We haven't had to do anything like that in the past few competitions. This is the actual post where he announced it, but he also announced what the actual microcontroller that we're using is. And so this is important because we can actually start development work now. We probably won't go super deep into it just because like if we like wanted all of you to start on this now, it would actually be horrible because you guys probably don't know what you're doing. So we're going to kind of have some people work on this on a back burner a little bit to the side. Yeah, question.
This one also like Teams before, or just like
This is not Teams before. This is unlimited team size. And it's just typically universities against other universities.
except for Purdue.
Except for Purdue. So actually, last year, Purdue had 3 teams. And the reason Purdue had 3 teams was because the main Purdue team that we usually work with didn't know that there was also a Purdue team that was from like some research lab there. Like they basically did not know each other. And they all just signed up.
Sure.
And so there was like 3 of them.
Likely story.
So the same thing could happen to us, but hopefully we've established our reputation here as the ECTF people. But yeah, so the microcontroller here is actually very new. It was released in 2024. It's new enough that there isn't as much stuff about it. I'll just quickly break down the name of it because it's a bit of a mouthful. It's the MSP M0L2228. MSP is, this is by Texas Instruments, by the way, but MSP is mixed signal processor, which is just sort of like the name that TI, Texas Instruments, assigns to their microcontrollers.
Mixed signal also says like analog and digital.
Yeah, analog and digital, yeah.
Actually, I see. Yeah.
M0 means that it's an ARM Cortex M0 Plus chip, which is the architecture of the chip. So if you guys have heard, a lot of you probably have x86 laptops if you're running Windows. If you're running Mac, you're running ARM. So these microcontrollers also typically run ARM because ARM is more power efficient. In particular, M0 is like one of the most power efficient architectures. L is low power, and then 2228 is going to be the part number. For purposes of, when I'm referring to this in the future, I'm going to be calling it the M0 chip. So, FYI. So this is a project that we're establishing here. If you have experience, you can feel free to join. If you're new, I recommend you kind of just watch because it's a little bit daunting to get started in this if you haven't had experience. But we want to write Rust, so we're going to have to sort of build the library that we're going to write the controller in Rust first before we can actually write the safe Rust code. So there's a bit of information about that there. The other thing we want to do is we want to be able to start glitching these microcontrollers reliably. So what we're going to do is
also just quickly, glitching is what voltage. All right, so there's a lot of terms that are referring to the same idea. So fault injection is a category of things that you can do that will induce like incorrect behavior on the processor. Voltage fault injection is where you mess with the power line of the chip, and that's also called glitching.
Yeah, so you think of glitching as like, you're like messing with the power to make it do bad things. But we want to get a head start on glitching so that way, because it actually takes a lot of time to get the right parameters, because you have to like pull the power down for this amount of microseconds and pull it back up, or maybe I have to change how powerful that glitch is, like pull it down to ground with more force. So this is the main thing that we want to do in terms of preparing for attacks in the future. If any of you know PCB design, we would love the help, because we want to develop an attack board basically to make this process go a lot easier. And also do side channel analysis on some cryptographic libraries with the chip running.
I mean, the idea is like we're provided the board on the left, and the board on the right is what actually will slot into the chip whisper, which is what's doing these attacks. So it's just basically adapting it for that platform.
Yeah. Does anyone have any questions about the chip stuff? I'm like going through it very quickly because I don't want to like make it a huge deal. I just want to let you guys know that it exists, and if you see it, there's like a channel we have dedicated for talking about it. Yeah.
Is there any risk of damaging the chip when trying to?
Absolutely. Yeah. So we will be, this is why like we will buy like a bunch of copies. We buy a bunch of copies so that way we can also give the microcontrollers for you guys to develop. But then later on, we're in the attack phase, so we're going to ask you to give the boards back, because we're probably going to start flying through them. The big thing is like we want to do it safely and reliably now, so that way when we're in the attack phase of ECTF, we can just do it and not have to figure out all the procedures. Yeah.
Did you talk about like manipulating the voltage like that? Are you talking about like manipulating signals to like, or like the voltage that's given to like certain memory, like bank or something like that?
So yeah, so basically, and we'll talk about this. We'll talk about the components of a microcontroller literally next next meeting. But the microcontroller has like sort of like you know how CPU has CPU cores? Yeah. A microcontroller also has cores. Usually each core on a microcontroller will have like a dedicated power line, and basically it might not be exposed externally like as pins, but usually you can find like something that you can tap into, like usually the main voltage line, and you have to remove resistors and capacitors because that can mess with the voltage as you're like glitching it. But if you do it right, then you can sort of manipulate that core power. And so it's not an exact science. Like literally the strategy to find a successful glitch is just run it in a loop and change the offsets one by one. Like we will literally have a triple for loop with like 3 different parameters that we're changing, trying to figure out the right parameters to get it to do what we want it to do. So yeah, it's a long process, but that's why we're trying to start it now. Yeah.
You don't use the same hardware. How do you like prevent against these hardware?
That's right. Say again.
If we all use the same set of hardware, then how do you prevent against hardware? Or is it like do we not use the same set of hardware?
That's a good question. So because the way it works is the organizers will send us the other team's firmware, which we flash onto a board that we have. So when we're attacking other teams' designs, we're going to flash the other team's firmware onto our board. So the idea is that if we can set up instrumentation on our own board ahead of time, then we could just do glitch attacks against every other team. Yeah. Oh yeah.
Well, it's like I'm like how do you like defend against like
So
stuff like this?
yeah,
It's
so
not the same,
I don't know when we're going to talk about this.
I mean, I can just briefly. So
Yeah.
yes, there are mitigations you can do in software if you assume certain things about what the attacker is capable of. So an example is we're talking about skipping instruction. If we say that the attacker skipped 1 instruction, we can duplicate the critical instructions so that they can't skip one of them and bypass the security check, for instance.
Yeah.
So those are the kind of mitigations that we're making. Yes, unfortunately, it is software, right? We can't be like buy a better microcontroller. Like that's not.
Yeah.
It's not what
Yeah.
we could, yeah. It's on the scope.
Yeah.
kind of like like both mine, like it's like close to, but if like also both of the two can be done like with hardware, but we're writing software to prevent that.
Mhm.
Like, how would that? Like, how would you stop?
So
Stop like them from like doing something with the hardware.
so you can't.
You can't.
You can't. So that's why it's important, and we're going to teach you these how to write mitigations against common types of attacks. Like as Jake mentioned, one thing you can do is you can do double, triple, quadruple checks to make sure that code executed correctly. If you have something like super critical that you're executing. Another thing you can do is you can randomly decide when to execute that instruction, because a lot of the voltage glitching relies on precisely timing where you're going to do the glitch. So if you randomize sort of or add random delays, it's a lot harder to do that. But there are ways to get around this. And it's kind of a game of cat and mouse. At this point, we're fairly confident that we know most of the tricks that teams are using in order to implement defenses. So again, this is why like ECTF is so cool, because like you learn about these random attacks and then you learn about these random mitigations to fix those things. And you're changing your software to fix the hardware issues. Not necessarily fix them. It's actually impossible to fix physics, but you can safely assume that at a certain point, a university team is not going to be able to do things with a certain level of precision. Yeah.
There's like codes that every time it senses like an external something, it just fries itself.
Yeah, so that's actually a rule. You're not allowed to do that. They thought of that.
Yeah, no hard block out.
Yeah.
The rule. But
Yeah.
in particular, the kind of mitigation you're describing is actually very difficult, like to monitor the voltage line. Because these are running for a very short period of time. Then whatever mechanism is actually triggering that, like
Is also like slow.
it's also liable to like not executing correctly in the case of a voltage injection attack.
So
Yeah, I mean, I think
we can talk a lot about voltage switching, but
I think like I don't know that like Raspberry Pi, like their microcontroller is they tried to make mitigations for these and like that are on the hardware level where it's like monitoring the voltage line and they have broken the mitigation. So it's quite challenging really to mitigate these fully.
so this is sort of wrapping up a bit, but we have some recommended readings. They're a little bit more on the technical side. I recommend the hardware hacking handbook a little bit more just because it has a little bit more words to ease you into things. But yeah, you're not required to read these. I just thought they were cool to have in case you wanted to learn more about this type of security.
Oh yeah, when CMU wasn't willing to tell us what they did to us, they told us to read the stuff.
Yeah. Yeah. There's some other resources like MITRE Embed. By the way, all these slides are on the site now. They should be. If they're not, yell at me. This is something you can look up in your free time. It's basically sort of like a checklist for embedded security systems, embedded systems in terms of security. Next week, we're going to have Embedded 101, the fundamentals. So we're going to talk more about the components of an embedded system before we start actually programming them. And then hopefully you guys understand why security matters now. So yeah. And again, mini content can be found